In this video, we'll be giving an overview to what we call the systems paradigm, which is the fundamental set of concepts that support systems theory and constitute this particular way of looking at the world. In order to try and give a clear understanding, we'll do this by contrasting it with the more traditional paradigm taken within modern science. This video will work as a high-level overview to what we'll be covering during the rest of the course. We'll be touching upon all of the main ideas here so as to get a sense for how they fit together, and then in later modules dig further into each aspect in more detail. A paradigm is a model, perspective, or set of ideas that form a worldview underlining the theories and methodology of a particular domain. The systems paradigm is then a coherent set of basic concepts and axioms that form the worldview or perspective underlining systems theory and thinking. All reasoning and scientific inquiry rests upon a set of assumptions or answers to fundamental philosophical questions. Before any kind of constructive inquiry into the world around us can be conducted, a number of basic philosophical questions need to be answered, including basic ontological questions, such as what is the nature of being, how does causality work, etc. Basic epistemological questions, such as how do we know something and how can we prove that we know it. Every coherent body of knowledge needs to provide some kind of answer to these questions, which will then form the basis for that conceptual framework, shaping how we see the world when using it, and ultimately the kind of answers that we can derive within that paradigm. For example, pre-modern European culture provided answers to these questions based upon a fusion between the work of classical Greek philosophy and the Christian Bible, among others. This worldview of medieval thought created a hierarchical ontology of things that existed based upon their perceived proximity to God. Those things, such as angels, that were regarded as closest to the perfect being of God, were placed at the top of the hierarchy, with humans below this, animals below them, and so on, all the way down to inert matter that was perceived as being at the lowest level and closest to hell. Within this worldview, epistemological authority or validity was derived from tradition. If it was endorsed by some pre-existing authority, such as the Bible, monarch, or Aristotle's writing, then it was deemed valid. This is a very simplified, schematic representation, of course, but it helps for illustration purposes. With the rise of the modern era, approximately 500 years ago, a whole new set of philosophical answers were formulated to these fundamental questions that still today form the foundation of our scientific framework. During a period of intense metaphysical questioning in the 17th century, a number of thinkers such as Francis Bacon and René Descartes laid the philosophical foundations to our modern world. These thinkers asked and answered the most fundamental questions about the nature of reality and knowledge, which were further fleshed out in the 18th century. They fundamentally rejected the idea that knowledge of the world around us should be derived from scripture, theology, or authority. These natural philosophers posited that the world is physical in nature, that knowledge about that world can be accumulated through empirical observations, that the laws governing this world were, as Galileo famously said, it is written in mathematical language, and its characters are triangles, circles, and other geometric figures, without which it is impossible to humanely understand a word. Without these, one is wandering in the dark labyrinth. Thus, a new paradigm and method for deriving knowledge about our world was formed, the so-called scientific method, where empirical data could be collected, hypotheses developed, and experiments done to validate or invalidate those hypotheses. In such a way, new knowledge could be accumulated, and it was believed that this knowledge should be put to the use of human betterment, to curing diseases, to growing more crops, to building bridges, etc. This new paradigm was most powerfully expressed in the work of Sir Isaac Newton, who did nothing less than describe a full mathematical and scientific framework for how physical systems interacted, the central idea of which was that of matter in motion causing events. that the world is governed by discrete components of matter interacting in a cause and effect fashion. Newton's absolute space-time coordinate system is the framework for a fixed, orderly, predictable, and deterministic universe, where all events are driven by the linear interaction of discrete components of matter, creating a mechanistic vision to the world, what is called the Newtonian paradigm. In a recent publication entitled Science and Culture, the author writes about the development of this new scientific paradigm as such. Science has had an increasingly strong influence on European culture. In the 19th century, the buzzword for science was order. Scientists had discovered that the movement of the stars is predictable, and that all terrestrial and celestial phenomena follow the same scientific laws like clockwork. They believed, according to the Galilean vision, that the book of nature is written in the language of mathematics, with characters represented by geometric objects. The vision of science was to discover the laws of nature and thereby explain all natural phenomena. This faith in science gave rise to the philosophical movement called positivism, which led to a widespread trust in science and technology and influenced social theory. This paradigm supporting modern science went largely unquestioned until the beginning of the 20th century, when quantum physics and general relativity showed its basic assumptions to be very much limited. By the start of the second half of the century, a new paradigm was gradually being formulated. This new paradigm we can call the systems paradigm, and it has a number of central concepts or axioms to it that work to counterbalance the traditional assumptions inherent within the Newtonian paradigm. The traditional paradigm of the modern era has posited a strong dichotomy between the subjective and objective. Since before René Descartes' formulation of a philosophy based upon a mind and body dichotomy, modern science has been strongly focused on the objective material world. Questions concerning the subjective dimension of the observer have been largely excluded in favor of a quantitative analysis of objective material components and linear interactions. This has resulted from the beginning in a strong divide between science and more subjective interpretations of the world, such as religion or many forms of philosophy. The systems paradigm breaks down this barrier, positing that the subjective dimension of the individual interpreter should be of equal importance to our understanding of the world. Systems thinking sees any knowledge of the world as a product of an interaction between the conceptual system used by the individual or community and the objective phenomena being observed. Thus, to gain a fuller understanding of the world, one must both question and develop the subjective framework being used as well as what's being studied. To do this, it is important that the assumptions, paradigm, and model used within an inquiry are made fully explicit so that everyone can examine the assumptions and bias that may distort the process. Systems thinking places great emphasis on recognizing and asking, how do I see the world? How do other people see the world? How do those models and assumptions that we all hold shape and create our interactions and the world around us? One of the central tenets of systems thinking can be summed up in the simple statement, we have met the enemy and he is us. That is to say, a recognition that how we see the world creates how we act in the world, which creates the world around us, which then feeds back to present us with challenges, all of which are the product of our subjective interpretation. Thus, for systems thinking, there needs to be a balanced emphasis on the subjective models and assumptions as on the objective inquiry that we're engaged in. Systems thinking is based upon a very different process of reasoning from that used in our traditional scientific paradigm. The Newtonian paradigm is understood to be primarily reductionist, which means that whole systems are seen to be reducible to an account of their constituent parts. Reductionism as a fundamental assumption leads to a process of inquiry called analysis. Analysis is a process of inquiry that proceeds by breaking systems down and trying to understand the whole in terms of the properties and interactions between its elementary parts in isolation from its environment. The analytical method has been central to modern science and accountable for many of its successes through isolating systems, decomposing them, and searching for linear interactions of cause and effect. Systems thinking is characterized as being what is called holistic, meaning that it always refers to the whole system or environment as the most appropriate frame of reference for understanding something. In order to understand some component or system, we must understand the context that it is a part of, its interaction with other systems, and its functioning within the whole environment. The process of reasoning that follows from this is called synthesis. Synthesis is the opposite from analysis in that it means putting things together. Synthesis is a method of inquiry used within the holistic approach, whereby we look at the relations between things and how, when we combine them, we get the emergence of new levels of organization. A central part of the analytical paradigm is the idea of linear causality. The primary endeavor of modern science has largely been to control for external variables, to isolate one or two input variables that are thought to cause some effect within the system. These cause and effect relations are encoded in equations and thought to describe how the system behaves. The central aim of the analytical paradigm is to ignore weaker influences from the environment and develop a model that is based on what are considered to be key observations, which are the primary driving variables causing change within the system state. Linear causality follows a sequential order where a direct link between cause and effect can be drawn, with there being a clear beginning and a clear end in time. Effects can then be traced back to one or a limited number of causes. This paradigm is extended to general reasoning when people see events as a product of some linear interaction from A to B to C, etc. Systems thinking, in contrary, is focused on nonlinear causality, where multiple factors affect an outcome, as they work together synergistically in a networked fashion to generate a combined result that is greater or less than the sum of their effects in isolation. A central idea here is that of emergence. With emergence, an event may not have any direct cause. Instead, within the systems paradigm, many events are seen as in fact emergent phenomena, not caused by any one thing, but instead they emerge out of the interaction between many things interacting in a horizontal, parallel, or networked fashion to generate the emergent outcome. Equally, systems thinking looks for circular or mutual causality, how two things affect each other, and how every effect feeds back to its source over time. Systems theory fundamentally rests on a relational or interactional view of the world. That is to say that the connections between the parts is explicitly given ontological precedence over the parts themselves. In the general sense, a system means a configuration of parts connected by a web of interdependent relations. When talking about any system, the emphasis is typically on the connections and interdependencies as the defining feature to the organization. The relational paradigm of systems thinking emphasizes how connections, interdependencies, and context shape the component parts of the system and not vice versa, which is the more traditional assumption. The traditional analytical paradigm is fundamentally component-based. Analysis is focused on the properties of things in isolation and how those things cause change through direct interaction. This perspective leaves us with a vision of the individual or component as the primary actor affecting change within their environment. It downplays the influence of connections and context in affecting and shaping the individual parts. Systems thinking helps instead to focus on how the network of connections around the individual parts and shape the system as a whole. This perspective becomes of particular relevance when the system comes to have a high degree of connectivity. The analytical approach is typically based upon excluding a changing environment, as described by the term ceteris paribus, which means all other things remaining constant. This static nature to the environmental variables makes it possible to repeat an experiment, to isolate and detect stable cause and effect interactions that are believed to be the drivers of change, which leads to predictable outcomes as long as it's possible to hold the environment constant. This is in contrast to the systems thinking paradigm, which is very much process-orientated in nature. It takes a dynamic vision of the world, where everything is seen to be fundamentally in change. This change is typically not perceived to be initiated by any of the particular parts to the organization, but instead is driven by processes that have inherent patterns that drive and shape the individual events that constitute them. Environments are seen to be complex and constantly evolving as a product of many interacting variables, leading to the emergence of new forms of organization over time. Processes of change can be driven by macro-level feedback loops that create certain dynamics and patterns of change on the macro level, what are called systems archetypes. Due to this feedback and emergence, change within the systems paradigm is seen as an evolutionary process rather than a mechanistic development. New phenomena emerge that could not have been predicted a priori due to the nonlinear interactions between the parts and their environments, and because of past events feeding back on themselves, all of which make the future essentially unpredictable in nature.